Instead, we'll just want to finish up Chapter 8 here and then talk a little bit about Chapter 9 and then just call it a day. But we see that the energies are now different, and what's the reason they're different? Because of shielding, penetration, and shielding. And what that means is the spectra are going to be much more complex. And so if we look at atomic spectra, if you look at the atomic spectrum here, what does this look like?
White light.
White light. You know, this is the full rainbow. This is what we call a continuous spectrum. This is from an incandescent light bulb, so just a regular tungsten light bulb. And we see the full rainbow of colors. Are there any forbidden energies? No, it's pretty much continuous. Okay, then we go to mercury. If you take a look at mercury, you see complicated lithium, cadmium. Potassium is funny. There's some kind of white light coming off this, so I'm not sure what happened to potassium. Strontium, barium. Let's go down, get a bit farther. Sodium. If you look at sodium, sodium is very simple. There are two lines here. Those two lines give this yellow-orange color, and so the sodium lamp that we had over here and the sodium street lights are the same. They give this yellow colored light coming off here from this. This is the sodium doublet, they call it. This line arises from an electron going from, I think, a 3p orbital to a 2s orbital. And then we have other lines in the spectrum which aren't seen for the other transitions. So there's going to be lines in the infrared. Is that right? No, infrared's over here. There's going to be lines in the infrared and lines in the UV for sodium. Okay. But the transitions, electronic transitions, get a lot more complicated because of all these energy levels. Now we have many energy levels. So that yellow line there, as I recall, is that a 3s to 2s? No, I think it's a 3p to 2s. Now there are rules in quantum mechanics. The rules in quantum mechanics are L is called the angular momentum quantum number. And so the s orbitals have a different angular momentum than the p orbitals, which have a different angular momentum than the d orbitals. And when we transition, when we think about angular momentum, we think about this motion of this. And when we transition for this, there are certain transitions that are allowed and certain transitions that are forbidden. So not all transitions are allowed. So for example, 2p to 2s might be forbidden or might be allowed. And so we've got to consider all those rules in addition to these. And then we can map out the spectra using arrows and an energy level diagram for this. Let's see. One more. So, this is for, what is that? Take a look at that. That's for hydrogen. And so very simple. This is for, I don't know what this is for, but this is for something more complicated. Do you see all the lines here, all the transitions that we have? And so certain transitions allowed, certain transitions forbidden, and we can generate a spectrum like this. And so the spectra obviously get much more complicated when we have more lines, and then there are certain restrictions on, you know, the direction of these particular arrows. So you can see this here mapping out the electronic transitions. Let's see, there's some others. You can see this. For example, a 1s to a 2s is actually forbidden. But a 1s to a 3p is allowed, or 1s to a 2p. This has to do with the angular momentum, you know, of the electron. And so one of the rules in quantum mechanics is delta L has to be plus or minus 1. And so this is why we get arrows like this here. But you can see the spectrum is going to be quite a bit more complex, correct? And, that's what's going to resolve. Now, what we're going to do next is this is the RDF. What we're going to do next is we're going to put electrons in the orbitals. We call this electron configurations, or if we start putting electrons in orbitals, we have to take into consideration one more quantum number. This is the spin quantum number, m sub s, or just call it s for short. And the spin, it could be plus 1/2 or minus 1/2. Electrons act as magnets, like this. And this was predicted by quantum mechanics. And so electron here, this would be called spin up or spin down. And these are the two possible orientations. So quantum mechanics being a theory, theories should be able to do two things. One, theory should be able to give you a fundamental description of, and this gives us a fundamental description of electrons and atoms. And a theory should also be able to do what? Make predictions. And so this is one of the predictions. One of the predictions of quantum mechanics is that electrons behave like little magnets. And so somebody went out to test this prediction, and the person that went out to test this prediction is Stern Gerlach. And so they devised this experiment where they're shooting silver atoms. When they shoot silver atoms through this, half of them end up here, the other half end up there. And that's due to their magnetic moment, you know, which direction the electron is, spin up or spin down. So they did that. This was easily detected in the Stern Gerlach experiment. Much later on, you know, it was predicted that the nuclei have spin too. Nuclei act like little magnets also. And so in the 1950s, a group of physicists went out to try to observe the nuclear magnetic moment. You know, they were unsuccessful. About 10 years later, another group went out and did the same thing. They were successful. The first group were unsuccessful because of electronics. In the 1950s, the amplifiers and that type of stuff wasn't very good. In the 1960s, technology had advanced quite a bit, and so it wasn't difficult for the 1960s physicists to observe it. Well, that observation led to the development of MRIs and NMRs, magnetic resonance imaging. So that's a significant development. So the Nobel Committee decided to award a Nobel Prize for the discovery of nuclear magnetic resonance, or magnetic resonance. And so this is an interesting story. I don't know if I ever said this. Did I tell you about this? So who got the Nobel Prize? Was it the first group that was unsuccessful because of the poor electronics? Was it the second group that was successful because the electronics got better? Or was it both the first group and the second group that won the Nobel Prize? It was just the second group. The first group was completely ignored, even though the first group were the first to propose the observation. And so this was one of those things. For people who are in the field of magnetic resonance, this was a kind of a failure, a big failure, the committee, to completely ignore the original physicists who proposed it. But anyway, that happens. And so what we're going to do is we're going to start filling these So for hydrogen atom, we only have one electron, so that one electron can go anywhere here. If the one electron's down here, it's what we call the ground state. Now, if we put the one electron, we'll put it as an arrow. You know, it could be an arrow spin up or an arrow spin down. If it's spin up, we call it plus 1/2. If it's spin down, we call it minus 1/2. So if an electron here is in the 1s orbital, we call it a 1, 0, 0, and depends on spin here. We'd call this electron a 1, 0, 0 because that's the orbital. It's a 1, 0, 0 orbital, and a plus 1/2. Whereas this electron would be a 1, 0, 0 minus 1/2 electron. Now there's something called the Pauli exclusion principle. The Pauli exclusion principle tells us that only 2 electrons may occupy the same orbital, and these electrons must have opposite spin, the Pauli exclusion principle. So that's one way of phrasing the Pauli exclusion principle. The other way of phrasing the Pauli exclusion principle is this. The Pauli exclusion principle says that no 2 electrons in the same atom can have the same set of 4 quantum numbers. Pauli exclusion principle. So no 2 electrons in the same atom can have the same set of 4 quantum numbers. The 4 quantum numbers would be N, L, M, and S. So we label it like this: N, L, M, and S. Sometimes the spin we call M sub S. Sometimes this, which was the magnetic quantum number, we call M sub L. But we'll just call it NLMS. And so if I tried to put another electron spin up, this would be a violation of the Pauli exclusion principle because that would have to be a 1, 0, 0 plus 1/2. There are only 2 spin states for an electron. And so that gives us a maximum capacity. The maximum capacity of an orbital is 2 electrons. And so we can't put more than 2 electrons in an orbital. Otherwise, it violates the Pauli exclusion principle, which comes from quantum mechanics. This is what we call the ground state. The ground state has the electrons in the lowest energy level. The off-bow principle is this. The off-bow principle is you fill the lowest energies first and then go higher. That gives you the ground state. But we don't have to have the ground state. For example, if we shine light on this, we might promote this electron to a higher energy orbital. So we might jump this electron from the 1s to the 3p. If we do that, that would be called an excited state. We've got 1 electron down here, 1 electron up here. Excited state. But if we want the ground state, we start off with the lowest energy and build up from there. Now, we saw the lowest energy is the 1s, or the 1, 0, 0, then followed by the 2, 0, 0, the 2s, and the 2p, 3s, 3p. But here, something funny happened. The 4s. The 4s is more penetrating, so the 4s actually dropped in energy below the 3d. Are there any other circumstances like that? Yeah, there are. There are a lot. So, for example, here, the 5s dropped below the 4d. And 5d. And the 6s dropped below the 4f and the 5d. And so there are a lot of these exceptions. So it's a lot to keep track of. So one thing is you can just memorize this up to 7p, but what do you do beyond? And so it turns out there's a pattern to this. And this is an off-bow principle. We want to fill the lowest energy electrons first. And so looking at the off-bow principle, we can figure out the filling order by using this pattern. And so the pattern goes like this. The pattern is going to be 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. What do you think goes next? 5g. Some people tell me a 5g orbital doesn't exist. Why? Because they've never heard of a 5g orbital before. Right? But there's an infinite number of orbitals. What is an orbital? An orbital is a loud state. 5g orbital exists because that's an excited state for an electron. You know, it's allowed, so it exists. All right, so if the pattern goes like this. it's 1s, and so we draw these diagonal lines, followed by 2s, 2p, 3s, 3p, 4s, 3d. So we caught the 3d coming after the 4s. 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, etc. So we can continue using this pattern. Although, is this a law? Not really, because there are some exceptions, you know. This is more like a rule or kind of a general observation. This is not a law. A law, you know, you'd have much fewer in terms of exceptions. Especially when we get to higher and higher energies. As we get to higher and higher energies, do you know what happens? Because we start off at 1s here. You know, in a hydrogen atom, the 1s is minus 2.179 times 10 minus 18 joules. But if we go all the way to infinity, up here, what's the energy at infinity? 0. And so this is not that much. And so between 4s and infinity, actually, how many sublevels are there in infinity? An infinite number of sublevels with an infinite number of orbitals. In other words, if an electron ever makes it there, it's what we call ionized. It's completely knocked off the electron. And it would be pretty much what we call a free electron. Free electrons have broken out of the box. If you break out of the box, then, you know what? You're allowed a continuum of energies. You know, it's just when you're stuck in the box that energy is quantized. Free electrons are continuous in terms of energy. But anyway, coming back to this, here we gotta put an infinite number. When you put an infinite number of lines here, the lines are going to get very close to each other. So as you get higher and higher in energies, you're going to find many more exceptions to the rule, right? And so you got to just be aware of that. Okay, so that's the opt-out. Then we worry about something called the Hund's rule. And so let's talk about the Hund's rule next, but first let's fill these. And so this is multi-electron. We want ground state. So should I put it spin up or spin down, or does it matter? Which one's lower in energy? The first electron. Should the first electron go spin up or first electron go spin down, or it doesn't matter?
It doesn't matter as long as the other one's the opposite.
As long as, yeah, it doesn't matter as long as the other one's opposite. Unless there's an external magnetic field. If there's an external magnetic field, then it matters, because they're going to be different energies. So let's say you have an external magnetic field out here, the North Pole's up here. That means it's lower in energy to orient the South Pole up than the North Pole up, because two North Poles repel, but North and South attract, right? And so it depends on the external field. Is there an external field? Yes. The external field is called the Earth's magnetic field. The Earth's magnetic field, however, is so weak that we don't really worry about it too much. You know? And so either spin up or spin down, doesn't matter. Most people write it, you know what most people write? The first electron, spin up. Now the second electron goes where? In the same, right next to it, spin down. And so this is 1, 0, 0 plus 1/2, 1, 0, 0 minus 1/2. And then we run out of room. So the third electron goes here. Okay, name this electron for me. That would be the 2, 0, 0 plus half. And then this would be followed by 2, 0, 0 minus 1/2. Now I have a choice. I could put it in the 2, 1 minus 1, I could put it in the 2, 1, 0, or I could put it in the 2, 1, 1. Which one should I put it in? Is the first one lower in energy than the last one? They're the same energy. We have 3 orthogonal p orbitals. It doesn't matter. One's oriented on the x, one is oriented on the y, one is oriented on the z, so it doesn't matter. But most people will put it in the first one, but I could have put it in the... And does it matter if it's spin up or spin down? It doesn't matter. But let's just put it in the first one. Now I'm going to add another electron. So this would be like beryllium, boron, carbon. Carbon has one more electron. Where does that electron go? Should it go in the 210 or the 211, or does it matter? It doesn't matter. You know, both of these are orthogonal. Both of these are 90 degrees to this, so both are equivalent. Should I put it spin up or spin down? Well, you know, it seems like spin down would be more favorable, right? North, but this is north-north, south-south. It doesn't seem as favorable, but it turns out this is lower in energy. And so that's Hund's rule. Hund's rule says that when we have energetically degenerate orbitals, then we fill these singly with parallel spins, not anti-parallel spins. And so it turns out if I put this one opposing spin, it's actually a higher energy than this. And this is the way the spins couple. And so we'll put it spin up. That's carbon. And then nitrogen has another electron. We'll put it like this. And so what are the quantum numbers? For example, what's the quantum number for this electron here? 2, 1. 2, 1, 1 plus half. And so the first three numbers tell us the orbital or the address. The last one tells us if it's spin up or spin down. And so we just need 4 quantum numbers to define this. Now, if we look at here, this is a filled shell. This is the filled n equals 1 shell. This is a partially filled shell. This is a valence shell. It's incomplete. But we can fill it. And so this would be nitrogen, I think, oxygen, fluorine, neon. Once we hit neon, then it's filled. So we filled the next shell. So this would be neon. This would be helium, like that. And these abbreviations are given to this filled shell configuration. And then we continue on, you know, continue filling these. This would be, now argon, what? Argon, does argon include the 3D? Argon does not include the 3D. And so the 3D's been left out. And so what we have here is we have the first shell, the second shell. First shell and second shell makes sense because we got the n equals 1, the n equals 2. But when we come to n equals 3, this shell is missing one. Seventh shell is missing the D. And so when we look at the third shell actually only consists of the 3s and the 3p. And once we fill that, then we're isoelectronic with argon. And these 3D actually aren't in this third shell. The 3D orbitals are actually in the fourth shell. Not only are the 3D orbitals in the fourth shell, but we also have the 4p orbitals. So the 4p orbitals go here. How about the 4D and the 4f orbitals? Are the 4D and the 4f orbitals in the fourth shell? It turns out not. And so a shell of orbitals is a set of orbitals with close energies. So the fourth shell is only going to consist of these orbitals here. The 4s, the 4p, and the 3d. Like that. Or the 4s, 3d, and 4p in terms of filling. So let's go ahead and start filling the fourth shell. In fact, when we start filling the fourth shell, let's take a look at this. Diagram. Now, I want to talk about different ways of expressing this. To draw this figure or this diagram out takes a lot of space. What was this one called again? What's this diagram called? Energy level diagram. This is the energy level diagram. Well, since it takes up so much space, Petrucci doesn't use this as much. Instead, he might use something like this. You know, this is called a condensed electron configuration. But when we go to condensed electron configuration, we lose a lot of information. One, we lose the information of the gap in energy between the 1s and 2s. Looks like all the gaps are the same. There's a 1s to 2s to 2p. Well, there's a big jump in energy. From 1s to 2s is a big jump, and a little jump in energy from 2s to 2p. Not only that, in a condensed, we don't know. We have 2 electrons in the 2p, but we don't know which orbitals. Is that the 2, 1, minus 1, 2, 1, 0, or 2, 1, 1? And so the condensed is short, but not as informative. And so this is a little bit more informative because here we have the 2px and the 2py, so they separate out. You know, let's say this is 2, 1, minus 1, 2, 1, 0. So they separate these out. And so we have one electron in the 2px, one electron in the 2py. But we don't know the spin up or spin down. And so in an orbital box diagram, an orbital diagram like this is better. And so Petrucci likes these orbital diagrams because they take up less space. If he had to print energy level diagrams like this, then the book would be a lot longer and be well over 1,000 pages. And so we do these, but these lack as much information as this. So on the test, which one do you think I'm going to ask you? I'm going to ask you to do the energy level diagram, because that's going to show me that you know the relative energies and everything else. But I might also ask you about these as well, because these are common, much more common. Okay. And so you in the homework you'll see a lot of these, but on the test I want to see this. Well, anyway, let's go back to this and let's fill up the fourth shell. So the fourth shell, we start filling it up here. Actually, we'll jump to the transition metals. So we're going to go from potassium to calcium. Potassium is going to have one electron in 4s. So this is what I'll do. I'll erase this. Let me clean this up a little bit. So we have all these orbitals, and then we go to the 4s. So what fills? It goes, basically this is argon up to here. And so we get 4s, and then 3d, and then 4p, like this. All right, so argon has how many electrons? 18 electrons. So the 19th electron would be potassium. And so potassium would be 1 electron here. And then after potassium comes calcium, so 2 electrons. This is 400 plus 1/2, 400 minus 1/2. And then we go here, not here, actually here, to scandium. Scandium, does it matter which one of the 5? No, it doesn't matter. So what are the quantum numbers for this electron here? The quantum numbers. The quantum numbers for this one will be 3, L1, 1. No? 3, 3. 3, 3. Minus 5. 3, 3 minus 5. Or plus 5.
No, 3, 2 minus 2.
Okay, 3, 2 minus 2. 3, 2 minus 2 is correct. 3, 2 minus 2. If you recall, the maximum L is 2. So this is 3, 2 minus 2, 3, 2 minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. Okay. So this electron would be a 3, 2 minus 2 plus 1/2. That would be our N, L, M, and S. L, M, and S. Let's do just a quick aside here. What would a 3, 3 2 plus 1/2 electron look like? A 3, 3, 2 plus 1/2 electron look like? Yeah, it would be the next one. The next one, well, we can figure it out because we did this earlier. L equals 0, L equals 1, L equals 2. The next one would be L equals 3. It doesn't exist. These don't exist. Why?
There are no 3s.
Yeah, because there's no such thing as 3f orbitals, right? That would be a violation of the quantum number restriction. The maximum L is n minus 1. So the maximum L for n equals 3 is 2. We could have 4f, no problem with that, but we can't have 3f. All right, so going back to this is scandium. And then we use Hund's rule. After scandium comes titanium, and then vanadium, and then chromium. But I'm going to stop at chromium because we're going to talk a little bit about symmetry. Let's imagine I have a cake. If I have a cake like this, there are two ways I can cut this cake in half. And so the two ways I can cut this cake in half, I can cut it down the middle like this, right? If I cut it down the middle like this, that destroys this circular symmetry I have, if I cut it down the middle. What if I cut it down the middle like this? If I cut it down the middle like this, then I retain the circular symmetry, right? And so if I cut it down the middle like this, then I have half the cake. But what if I take a slice of the cake out? If I take a slice of the cake out, then I've just ruined the circular symmetry. It turns out that circular or spherical symmetry is important because it leads to lower energy. And so a weird thing happens with chromium. The weird thing that happens with chromium is that the 4s electron gets bumped up to the 3d. And so for chromium, we expect this. We expect argon, this is electron configuration, 4s2, 3d4. But when I see 3d4, that's a half-filled cake with a slice taken out of it. And so what we can do there is we can rearrange this. We can go, chromium's going to have argon, 4s1, 3d5. Now 3d5 is great because we get the circular symmetry back. And this is not circular symmetry. If we have d orbitals, all 5 d orbitals half filled, that's what we call spherical symmetry. So if you look at 3p orbitals, if you have 3p orbitals and they're all filled or half filled, we have spherical symmetry because it's x, y, and z. And the same thing with the d orbitals. If we do that with all the d orbitals, this is spherical symmetry. And so we say that there's half-filled D sublevel has spherical symmetry. So half-filled D subshell or sublevel is spherically symmetric. Spherical symmetry, which leads to additional stability. And so that works. Well, that's what's observed. This can be experimentally measured. What about that? That was, hey, vanadium. Vanadium is only 2 electrons short. So if I take both of these s electrons and promote them here, then they'll be half filled, right? But to take both of the s electrons and promote them takes too much energy. And so we can only promote one because that's all we have in terms of energy. Okay, so chromium is what we call an exception to the filling rules. It's an exception because of the stability of the half-filled D subshells. But when we go from chromium, what's after chromium? Manganese. When we go to manganese, then we're back to normal. We can have a half-filled D subshell and a filled S rather than half and half. And so we'll go manganese, and then we continue across until we get here. When we get here, what element is that? And this is the element 4s2, 3d9. And this element also starts with a C. This is copper. Take a look at copper. Copper is taking the full cake. So if we take a full cake like this, and then just remove one slice, we're just one electron away from a filled D subshell. A filled D subshell is going to be spherical symmetry here. And so what happens in copper is the electron gets promoted. It's just one electron gets promoted up here. And so copper we expect to be 4s2 3d9, but copper ends up being 4s1 3d10. That's for half. Now, why did they write it backwards? Why did they write the 3D first and the 4s next? Here, 3D first and the 4s next. Because you can write it either way. They write it backwards because they're showing something else. If we're showing how they fill, we fill the 4s before the 3D. But, actually this is wrong because this is correct. But we could also write it like this. We could write it argon 3d10 4s1. Do you know why we write it like this? We write it like this to show something. Yeah. We write it like this to show the what we call the valence electron. What is the valence electron versus the core electron? The core electrons are defined as inner shell electrons. Valence electrons are defined as outer shell electrons. Right? But when we think about this, aren't the 3D farther out than the 4s? Look at the 3D are farther out, aren't they? The 4s are closer in. But this is in terms of energy, not in terms of distance. In terms of effective distance, the 3D are much closer to the nucleus than the 4s. It just so happens the 4s are more penetrating, dropping their energy down, but the distance is still far out. And so if you're an oxidizer, this is it. Let's say you're plucking apples off the tree, and there's an apple here, it's close by, but it's harder to pluck off. But there's an apple further up the tree that'll be easier to pluck off. And so what should you do? Should you take the apple down low that's harder to pluck off, or should you try to reach the apple up high that's easier to pluck off? Maybe you would try to reach the apple up high. But if you're an oxidizer, do you care? If you're an oxidizer, do you have a brain thinking, which apple is going to be easier to pluck off? No, an oxidizer is going to attack the electron that is closest. And so if you're an oxidizer coming to attack copper, are you going to try to pluck off a D? Hey, a D is going to be easier to pluck off because it's going to cost less energy. You know, because the D is already higher in energy, so I'm going to pluck off an electron, bring it to infinity, and take it off, right? Are you going to try to get a D because a D is easier to pluck off? An S is going to be a little bit harder to pluck off, but it's closer. That's a little bit harder to pluck off, but it's closer. And so what do you think? Is an oxidizer going to weigh the pros and cons of this, or is it just going to attack whatever electron it sees it's nearest to? It's just going to attack whatever electron it sees is nearest to it, and if it can't pluck any of these off, then it'll try to pluck those off, right? I mean, if it can't pluck any of these off, it'll try to pluck these off, right? And so it turns out that it's written this way to show how these react. And so an oxidizer comes in and plucks this electron off, giving copper what charge? +1.
So I'm confused. When you have copper and you get argon, you know how it says 3D to 3D10 or S1. So like, how do you get that? Like, I get it, you're supposed to go backwards, but like,
These two are the same, basically. One, are you comparing these two, or are you asking why it's a 1 and 10, 10 and 1?
I'm asking one. Like, how do you get it?
Oh, how did I get the numbers here? The numbers come from this. The numbers come from, you just made a beautiful cake, let's say. And it has nice symmetry to it. And then all of a sudden, somebody takes half the cake. They just cut it like this. Move it. What just happened to the symmetry there? The symmetry was destroyed. You no longer have the symmetry. And so there are two ways we can half-fill the orbitals. One way we can half-fill the orbitals is like this. Is this stable? Tell me how stable this is going to be. You tell me how stable this will be. I'm going to slice it down the middle like that. And so altogether I can put 10 electrons here. Slice it down the middle. So I'm going to remove this half of the electron. Right? So I remove this half of the electron because I want half the cake. So I'm just going to cut it down the middle, take these, leave these. Is that stable? Is that stable? So I just removed half the electrons. It was a full cake, now it's half a cake. Is that stable? No. What would be more stable? If I took the 5 electrons and put them all on one side, or if I took the 5 electrons and spread those out in 3-dimensional space spherically to separate them as far apart as possible so that they don't, because electrons are, actually this is 6, sorry. Is that 6? 1, 2, 3, 4, 5, 6, sorry. So that they don't, because electrons are negatively charged, so they don't, because electrons, do you think electrons like electrons? No, electrons like protons. And so if you crowd the electrons too much, are they happy? No, they like to spread out. And if you want to spread out, how can you spread out the farthest? Well, you think about a sphere, right? And you get that spherical symmetry. And so this is what I mean here. That's one way of maybe thinking about it. Another way of thinking about it is this. Now, this turns out to have some, stability due to being half-filled and spherically symmetric. And so what I can do now is I can upset that symmetry by removing an electron. If I remove an electron here, is it still evenly spread out, evenly distributed in this spherical arrangement? No. And so if I have 2 electrons here, these 2 electrons are kind of crowded. These 2 electrons are a little bit crowded because now these 2 electrons are in the 4s orbital. But if I could just kind of promote this electron up here, then I can spread out and get some more breathing room. Does that make sense? And so what happens is this. In other words, you don't have to understand this at all. All you have to do is memorize this. Half-filled D is stable, so we like it. A filled D is stable, we like it. And so there are going to be 2 things that happen here. Chromium and copper have very weird filling. Look at chromium and copper. Do you see that? What happened to the S? All these have 2s electrons. What happened is chromium came up 1 electron short of half filled. And therefore, an s electron got bumped up to the D to half fill it. And so we have stability in the half filled D. In copper is 1 electron short from a filled. And so what happened was the s electron got bumped up to D to fill this. And so there are 2 exceptions here that you have to memorize, chromium and copper. Those 2 exceptions carry on because what's below chromium? Manganese. Manganese has, or molybdenum, sorry. Molybdenum has the same exception. What's below copper? Silver. So if I look at silver's electron configuration, let me show you what it is. Silver will be krypton. So if I look at silver metal, it should be krypton, 5s2, 4d9. But if you look at 4d9 you'll recognize is 1 electron short from being filled. And so what we'll do is silver turns out to be krypton 4d10, 5s1. Giving silver how many valence electrons? How many valence electrons does silver have? Silver has 1 valence electron. If you're an oxidizer, which electron are you going to attack? Do you think you're going to have any success at pulling a 4d electron off? No, this is filled, it's symmetric. And so you're going to have success pulling this off. And so if you're an oxidizer, you're going to remove that 5s1 and you're going to form Ag+. Ag+ is going to be krypton 4d10. That's it. So basically there are more exceptions, but we could use the periodic table to figure these out or try. And so copper, silver, gold, you know. But as we go to bigger and bigger shells, what happens is the orbitals get more and more compressed. So that there become more exceptions because it doesn't cost that much to promote the electron to higher energy levels. So you see different versions of the periodic table depending on what happens here and you know the energy differences in the orbitals. But what we can do is we can use the periodic table to make predictions because the periodic table is based on these orbitals. You've got the s orbitals here, the d orbitals, p orbitals, f orbitals here. And so let's pick something more difficult. Let's pick europium, element number 63. If we want to figure out how 63 fills, then we'll go back here. We'll probably start at xenon. Xenon has 54 electrons, so we go from 54 to 55. And so this will be 6s1, 56 will be 6s2, and then we go to 57. They're telling us 57 drops here. So we go 6s2 to 4f1, 4f2, 4f3, all the way to 4f, is that 6? Is that right? 6. Yeah. And so we can get europium. What about if we wanted something like, let's say, RF? Anybody know what RF is? Rutherfordium? Okay, if we go to Rutherfordium, I didn't even know that. Rutherfordium, we're at element number 104. So to figure out the electron configuration for that, we go to radon, 86. And then 87 would be 7s1, 88 would be 7s2. And then what do we do for 89? It says drop down here for 89. So 89 would be 5f. We'd fill this up to 5f14, and then we're at 103. And then from 103, we go back up here. And so now we're at 6d1. And so we could use the periodic table to figure out electron configurations as well. And so the periodic table is based on the valence electron. So this is why we write this here. So if I look at, let's go to iodine. What are the valence electrons on iodine? Can you tell me what the valence electrons on iodine are? What are the valence electrons on iodine? Iodine's krypton 4d10, 5s2, 5p5. What are the valence electrons on iodine?
What is specific?
Or just in general, what are they? Well, you know that iodine has how many valence electrons? 7. And so what are those 7 electrons? Well, those 7 electrons are the 5s2 and the 5p5. These are the valence electrons. The valence electrons are going to be the electrons in the highest n level. Those are going to be the electrons that are furthest out. Now, the 4d are considered core electrons. In this case, the 4d are filled, but they don't always have to be filled to be considered core electrons. Same thing. If we go to actinium, what are the valence electrons here? How many valence electrons does it have? 7 again. Right? The 6s2, the 6p5. If you're an oxidizer, you're going to pull the electrons that are furthest from the nucleus first. And these would be considered core electrons here. Now, the same thing happens with the F. We have a filled F subshell, so that's going to be stable and hard to break, that symmetry. But anyway, we see that the periodic table is going to be organized according to valence electron and valence electron configurations.
Yeah.
Yeah, that's chapter 8. And so what we're going to do is chapter 9 is a continuation of chapter 8. And so let's just dig into chapter 9 a little bit, and then we'll call it. Who first came up with the periodic table? Yeah, Mendeleev came up with the first. Well, probably other people did too, but he's largely credited with the periodic table, right? And so Mendeleev was 1834 to 1907. Is Mendeleev the father of quantum mechanics? Because the periodic table is based on quantum mechanics, right? So, no, quantum mechanics came after Mendeleev. But how could Mendeleev come up with the periodic table without quantum mechanics? Because the periodic table is based on orbitals. Orbitals come from quantum mechanics. Magic? Or was he a prophet? Or
Kind of. He predicted that there was going to be a revolution.
yeah, right. Mendeleev predicted. What did he predict? Eco-silicon. Let's go here. Eco-silicon. Missing element. Eco-silicon turned out to be germanium. But Mendeleev came out with the periodic table because the periodic table was based on patterns, on properties. And so we can see that the periodic table, if we look at some of the patterns, one of the patterns is volume, molar volume. If we look at molar volume, we can see that molar volume shows this periodic trend, like the periodic table. Molar volume, we're not really going to spend much time with molar volume. And so it's the properties. Okay, but we know that it's based on quantum mechanics. So we see this. This is the X-ray spectra of different elements. So if we look in the X-ray region, we knock off core electrons, and valence electrons drop down to produce light. That light is high energy, X-rays in this case. And so if we look at the X-ray spectra, this is just more quantum mechanics. We can see, like brass. Brass is a mixture. Do you know what's in brass? Well, copper is in brass. Do you see? If we look at the X-ray spectrum for copper, we see a line here, thick. Well, that's shown in brass, and then another line here shown in brass. But brass, there's something else in there. Do you see this line and this line?
Yes.
But we don't see a match here. We'd have to look for other elements. Do you know what it is? Tin or zinc or aluminum? Well, it depends on the brass. And so here we can see again that each of these have a unique spectrum, and so these can be used to identify the element. In fact, the lunar lander had an X-ray spectrometer on there, so it can analyze the elemental composition of rocks. And so here we have the periodic table. The periodic table is broadly divided based on properties. So on the left we have the metals, right? On the right we have the nonmetals, and this green is called the semi-metals. The metals all share similar properties. Metals are good conductors of heat and electricity. They're malleable, ductile, moderate to high melting points. And so all metals share pretty much these properties. Non-metals, the properties vary a lot more. For example, helium's a non-metal, and fluorine's a non-metal, but the properties differ dramatically. And so that's a little bit more difficult. Metalloids have properties of both. We know that metals tend to lose electrons. They lose electrons to be isoelectronic with the nearest noble gas. So group 1 will lose 1 electron, group 2 will lose 2 electrons, group 3 or 13 will lose 3 electrons. Group 4 should lose 4 electrons. But when we start to get to 4 electrons, that's a lot. Group 5 should lose 5 electrons, or 15. Those charges are easy to predict. These charges are the nearest noble gas. Then we have pseudo-noble gases, like silver. Silver, this is what's called pseudo-noble gas because it's not quite noble gas. Noble gas would be krypton. In order to be noble gas, silver would have to lose 11 electrons, the S and the 10 Ds. But is it going to lose these 4d10 electrons very easily? No. And so this is why we call it pseudo-Nobel gas, because the 4d10 is a filled subshell which is stable, just like the filled shells are stable. Noble gases are very unreactive because of the filled shell configuration. And so we have that. That's pseudo-Nobel gas. And then what we have are the 18 plus 2. So if we look at 18 plus 2 is like lead. We can predict the charges on lead quite easily. What's the common charge? The common charge on lead, we can see, what are the two common charges of lead? Lead is, well, let's look at lead itself. What's the electron configuration for lead? If we look at the electron configuration for lead is going to be xenon. So if lead is xenon, just read it out for me. So xenon and then 6s1, 6s2. And then from 6s2 we drop down to 4f14. From 4f14 we drop back up to
5D.
3d45d 10. From 5d10 we go to 6p2. So one of the common charges on lead is lead 2 plus. Which electron do we lose? The 6p2. And so the electron configuration for lead 2 plus is we just lost these. What's another common charge? Lead plus 4. If we do lead plus 4, what electrons did we just lose? Yeah, we lost the 6p and the 6f. And so this is why it's rewritten. It's rewritten like this. It's rewritten in numerical order to show the order in which the electrons are going to react. And so even though we don't fill it like this, we're looking at this reacting. If you're an oxidizer, you're going to come and take these electrons first, plus 2. And then you're going to take these, plus 4. How about, is lead plus 5 common? No, because you'd have to break the D. That's not going to happen. And so this is what we call the 18 plus 2, but you don't have to worry about 18 plus 2 because the numbers don't add up so nicely. And you can see that in the footnote here. And the others. The others are one of the most common charges: chromium 2 plus, iron 2 plus, cobalt 2 plus, nickel 2 plus, copper 2 plus. Why 2 plus? Because it loses the s electrons first. This loses 4 s electrons. And then if we go plus 3, then we can start losing D. This is not a filled D. So if we're looking at iron is argon, 4s2, 3d6. And so iron 2 plus is very common. Iron 2 plus is going to be argon, 3d6. Now 3d6 doesn't have, is that half filled or filled? Well, we can lose another electron. If we lose another electron, we get argon, 3d5. Well, 3d5, we know that's half filled. So we'll probably stop there, right? But it doesn't have to go half filled. It doesn't have to be half filled. So those are in the other category. Now nonmetals will gain electrons. So the halogens gain 1, the chalcogens gain 2, the nitrogens gain 3, or the oxygen family and the nitrogen family. Carbon would gain 4, the carbon family. to be like the nearest known gas. And so here we can see some transition metal ions. Iron, iron plus 2, 3d6. Iron plus 3 is 3d5. Hydrogen can either gain or lose, but typically it loses. So hydrogen is most likely a reducing agent. And so it's most often placed in group 1, but sometimes it's placed in group 17. In our periodic table, it's placed in both group 1 and group 17. Okay, then we're going to talk about atomic radius. Atomic radius is tricky because the atom does not have a hard shell. The atom, if I try to probe the size of the atom, it's mostly empty space, right? Empty space in which electrons exist. So if I want to probe the size of a hydrogen atom, I'm looking at an electron cloud here. So let's say I have a probe even smaller than an atom, a hydrogen atom. It's not possible, really. But if I have a probe, am I going to hit something? I'm going to hit nothing. I'm going to push this in until I get significant repulsions from the nucleus or whatever. And so there's no solid surface. I'm just going to meet resistance. Greater and greater resistance due to the repulsion. And so what do I call the size? Should I call the size the 95% boundary? Should I call the size the most probable distance? Should I call the size the effective distance? No, none of those. What I'm going to call the size is this. I'm going to have different sizes depending on how it's bonded. So let's look at sodium. If I can make a sodium molecule consisting of 2 sodium atoms, then what I'll do is I'll pinpoint the nuclei. But is it possible to pinpoint the nuclei's position? Because we have the Heisenberg uncertainty principle. Is it possible to pinpoint where the nuclei are in 3-dimensional space? And you think not because of Heisenberg uncertainty principle, but the nuclei are massive compared to electrons. And so it turns out that the uncertainty of the position is negligible. And so we can pinpoint where the nuclei are. If we pinpoint where the nuclei are, then what we'll do is we'll take the nuclei to nuclei distance. In other words, we call this the bond distance, and divide it in half. If we divide it in half, we're going to call this half the radius, and this half the radius here. And so in a sodium molecule, the radius is 157 picometers because the bond distance is double that. However, in sodium metal, because there are other sodium atoms out here, in sodium metal, the bond distance is longer, so the radius is longer. And so the size is bigger. In the sodium ion, the size is smaller. And so we see the size varies depending on the bond. So we're going to have different radii we're going to deal with. And so what we do is we kind of average those. We kind of average the covalent radii and the metallic radii and come up with the radius. And this is the trend that we see in the radii. The trend is, if we start at lithium, lithium is big compared to fluorine. And so it goes like this. Lithium to beryllium shrinks, beryllium to boron shrinks, and continues shrinking until we get to fluorine. Fluorine's a very small atom. Do you see that? And then we go to sodium. Well, going from lithium to sodium, the size jumps up, and then it shrinks. But that doesn't seem to make sense. And so let's visualize this here. We're looking at the gold. And these are the size of the... Why is fluorine smaller than lithium? Fluorine's got more stuff. Fluorine's got more protons, more electrons, and more neutrons. And so why is fluorine... Shouldn't fluorine be bigger if it has more protons, neutrons, and electrons? It should be bigger because it's got more stuff, but it turns out it's smaller. And so why is that? To understand why that is, we have to understand this. Shielding or screening and penetration. That's the title of this. This is the atomic radius. Why do we have to understand shielding and penetration in terms of atomic size? It's because of this. here we can see shielding. Basically this. The reason why fluorine is smaller is we'll look at it from this point. We'll ignore this diagram for right now. What is that diagram? What are those? What's that? These graphs. RDFs, right. Yeah. And so let's take a look at lithium first. How many protons does lithium have? Let's look at Z. It has 3 protons. And so Z is going to be plus 3, let's say, 3 protons. If we go to beryllium, beryllium has 4, so it's plus 4. And so we go from plus 3 to plus 4. But we also add an extra electron. When we add an extra electron, that electron turns out to be same shell. Is the same shell electron effective at shielding? Because this is a 2s orbital. No. And so even though we add an extra electron, that extra electron doesn't cancel out the Z. So what happens is Z effective increases. And so Z effective is increasing as we go across. And so we go plus 5. Well, we add an extra electron, but that extra electron is in the same shell for boron. So boron's going to shrink. And so lithium starts off as the biggest, then beryllium's smaller, and then boron's smaller. Plus 6, we add another same shell. And so even though we're adding both a proton and electron, the electron doesn't shield very well because it's the same shell, and therefore Z effective increases, and the atoms shrink going left to right. Same shell. And so here we can see, if we add a same shell electron here, they aren't effective shielders. However, if we add an inner shell electron, it would be an effective shielder, blocking out the 3. Let me see. I'm just going to keep talking and just try to finish up earlier. And so here we can see it here. Same shell electrons aren't very effective at shielding. However, if I have an inner shell electron, those are effective at shielding. So let's go back to this. This is exactly what I see here. So across the first period, we're adding this. Now, the jump from lithium to sodium sodium has another shell. And so having another shell of electrons means it's going to be bigger. And so here, we expect this to be bigger. But again, once we get to sodium and we go across to chlorine, chlorine's smaller. And then same thing, we start off with potassium, bromine's smaller. What do you think the smallest atom on the periodic table is? Is it hydrogen or helium? Is hydrogen or is it helium? Which one is smaller? Well, a lot of people will say hydrogen. Why hydrogen? Because hydrogen consists of 1 proton and 1 electron. That's it. But it turns out that hydrogen is bigger than helium. Why? Helium's smaller. Helium is smaller because helium has 2 protons and 2 electrons. And it turns out these are same shell electrons. And so if they're same shell electrons, then this electron isn't very good at shielding from this, and vice versa. So what's going to happen is now the electron sees plus 2. Over here, this electron sees plus 1. If this electron sees plus 2, that's going to pull the electrons in closer and shrink the size of the atom. And so this is it. It has to do with shielding and penetration. Now, we get to something strange, though. Do you see this flat area? What's going on with that flat area? And so let's take a look at this to gauge. That flat area is occurring here in the transition metals. So let's take a look. Chromium, 128 picometers. Manganese, 127 picometers. Iron, 126 picometers. Cobalt, 125. Nickel, 124. Do you see how flat that is? There's no change. It should be shrinking because I'm adding a proton. So from chromium to manganese, I'm adding a proton. Manganese to iron, I'm adding a proton. I'm adding protons, more protons, so it should be shrinking, but it's not shrinking. Why is that? And so let's pick two of these. We're going to pick, let's pick cobalt and nickel. Cobalt's 125, nickel's 124. Essentially the same size, 125 and 124. And so when I look at cobalt versus nickel, nickel is plus a proton and plus an electron. And so if it's plus a proton, it should shrink more because Z effective is increasing, isn't it? But we have to think where this electron's going. This electron is going into the 3D subshell. And so if we think about nickel, what's the outermost electron in nickel? Well, nickel is this. Nickel is going to be argon, 3D8, 4s2. Cobalt is argon, 3D7, 4s2. So what happens here is we add a proton and we add an electron, but that electron is not going into the outermost shell. That electron is going into a inner shell. And what did we say about inner shell electrons? They shield effectively. And so even though we're adding a proton here, we're adding an inner shell electron because 3D are inner shell. They're closer to the nucleus. And those are going to effectively block out. And so the radius doesn't change because of shielding. And,
Why does copper grow?
copper, well, it grows, but by how much? I mean, these sizes, remember, the sizes, are these hard shell? Are the sizes consistent? No, and so these are pretty much flat line. You know, even though, yeah, it grows a little bit, but it depends on the compounds you measure because these are actually experimental measurements. Are experimental measurements so exact? So, for example, if you're measuring the pH of something, or if you're, well, I shouldn't say pH because we haven't gotten there yet, but if you're measuring something, is it so exact that, you know, or is it subject to error? Whenever you take measurements, all measurements are subject to error. These numbers are from measurements. These aren't from any kind of theory. These are averages of that. And you saw the variation with sodium. And so somebody else measures some other compound that contains cobalt or iron or copper or whatever else, and they're going to come up with a different radius. You know? And so it swings one way or the other. And so here, actually, we see a decrease, 162 to 147 to 134. So it's like a U here, a little bit. But once we're past this U, take a look what happens. I mean, it's not perfect because there are other factors that happen, but essentially this is it. You know, add electron. And so the end result is this. The end result is the smallest atoms are at the top right. So helium would be the smallest. The largest atoms are at the bottom left. Okay? Size decreases going across. Like so from sodium to chlorine, size decreases. Why does size decrease? Size decreases because you're adding a proton and you're adding a same cell electron. So if you're adding a proton, Z effective is going up, and the same shell electron doesn't shield very well. And so size decreases. So size decreases here. Size decreases and then flattens out. It flattens out because in the D block, you're adding a proton, but you're adding a inner shell, because this is 3D. This is 4s going to 3D. And then we go to 4p, and the size trend continues. So there are going to be small variations here. Now, the size jumps from here to here. The size jumps from here to here because the shielding's about the same. You know, if we look at the inner shell electrons that lithium has, I'll stop soon. If we look at the inner shell electrons, lithium has 3 protons, correct? So it's +3. How many inner shell electrons does lithium have? It has 2 inner shell electrons, and then it has 1 outer shell. And so what's Z effective? We're not going to follow Slater's. We're just going to do the simple one. Z effective is +1, right? Now let's go to sodium. Sodium has, what does sodium have? "11 protons. Sodium has 11 protons, and it's got 2 shells, the helium shell and the neon shell. In the helium shell, we have 2. In the neon shell, we have 8. And so altogether, we have 10 inner shell electrons. And then we look at the outermost electron. What's Z effective on the outermost electron? Z effective is +1. And so when we're in the same family, Z effective doesn't change. It changes a little bit because of Slater. It changes, but essentially it doesn't really change much. What changes is we're adding another shell. Adding another shell is going to make the atom bigger. And so this is the reason why the size increases. Even though we're adding a lot of protons, we think adding, how many protons did we add? We went from +3 to +11, so we added 8 protons. If we add 8 protons, isn't that going to be like a tractor beam and pull in all the electrons? No, it doesn't, because we added 8 protons, but we also added 8 inner shell electrons. Okay, and so that's atomic radius, and I'm going to stop here. Sorry, I went longer than I was expecting.